Hi everybody, my name is Vivek Anand and I'm a part of the Ashton Graybill Spatial Orientation Lab, and I'm also a Translational Research Institute for Space Health postdoctoral fellow. Now, my main objective for today is to provide a holistic view of my research, really showcasing how human spatial disorientation may have relevance to a variety of different fields, from like neuroscience to dynamical systems and physics and math, maybe even a sprinkle of chemistry, and also relevance to psychology, computer science, things like that. So this will be like close to a 30-minute talk. If some of you have to leave towards the end of that, totally no stress there. The second objective is really to hopefully engage or excite some of you so that you reach out and we do some multidisciplinary collaborative discussions, because those are some of my favorite things to do. Now, this next part I'm not going to be doing today, but this is part of the original vision that got Zoom bombed, which was that then we take ourselves, put ourselves in randomized breakout rooms and really begin to socialize and idea generate and explore that. So if any of you are interested, I'm always happy to reorganize that. So I'll begin my presentation today with my usual storyline. Imagine that you are an astronaut on your way to Mars, and you spend months and months and months in zero-G in outer space, where if I blindfold you, the concept of up doesn't even exist. I just want you to absorb that, because it's a pretty crazy idea. Like, every moment of our lives is saturated in knowing where up is, and all of a sudden that's gone, and you spend months like that, and then comes a day when you have to land upon the surface of Mars, and all of a sudden knowing where up is a matter of life and death as you try to stabilize that spacecraft when you're landing upon the surface. And what we know is that in that gravitational transition from zero-G to Mars-G, astronauts will become very susceptible to spatial disorientation. And all that means is, spatial disorientation means when you have difficulty telling where you are relative to the upright. Now, just to highlight what significant amount of problem this is, like, you can forget Mars or the moon. The leading cause of fatal aircraft accidents in military pilots, this is where they're dying, is spatial disorientation. So it's not fully understood. We don't have solutions that definitively work. And that's really where my research comes in. I try to create a spaceflight analog condition here on Earth in a Brandeis lab, where subjects can't use gravitational information to do the task, and as a result they become spatially disoriented. And I kind of want you to think about this so that it's exciting for you. Like, how would I recreate that on Earth in a lab, a spaceflight condition? And the way that I do it is I strap people into this machine. Now, this first condition is not my spaceflight condition. This is my control condition. People have a pretty good understanding of where they are. I'll describe this first, and then I will reveal the spaceflight analog condition. But basically, I take people, I strap them into this machine, and the machine is programmed to behave like an inverted pendulum. And all that means is if you do nothing, just like trying to balance a pen on your fingertip, it just sort of falls over. So it's programmed to naturally fall over to the left or right. There are crash boundaries so that if you go too far, the machine stops and then automatically resets to the balance point, and the experiment begins again. Now, what I tell subjects to do is grasp that joystick and use it to stabilize themselves and really minimize oscillations and variability around that balance point. And an interesting side point is that because they're seated and they're using a joystick and not their legs, and therefore they don't have access to the biomechanical properties or reflexes of their legs, this becomes an interesting window into central processing where peripheral mechanisms are not in the loop. So if you're interested in that perspective, feel free to definitely reach out and talk to me. Now, in terms of the sensory information that they're receiving when they're doing this task over here, you can see that here I'm blindfolded and I'm wearing noise-canceling headset. And as a result, I can't use my visual system or auditory system to know where I am. Primarily, the sensory information that I'm receiving about where I am is through my vestibular system, which I'll describe in a second, and then to a secondary extent, my somatosensory system through the touch receptors on my skin as I push against that machine. Now, the vestibular system, to understand it, we're going to take a magic school bus ride into the inner ear. And in the inner ear is your vestibular system, and your vestibular system has two components to it. The first are your semicircular canals, and these are canals filled with fluids that have little hairs in them, and what they detect is angular acceleration during rotation. So when I, for example, rotate my head like this, I'm activating these canals. Really, all I want you to take away from this is that the canals are detecting motion, acceleration. That's the main piece of information that they're getting. The second part of the vestibular system are your otolith organs. And your otolith organs are these fine little hairs suspended in gelatinous material adorned by beautiful crystals. And what they detect is linear acceleration. And really all I want you to take away from my presentation is that they detect tilt from gravitational vertical. The more you tilt from gravitational vertical, which is where my balance point is, the more those hairs deflect. So you get a really good sense based on how much your hairs are deflecting on how far away you are from the balance point. And to sort of re-summarize the sensory information that you're getting in my control condition, the upright condition is you have a good sense of position because the more you tilt from the gravitational vertical, which is the balance point, the more those hairs deflect. You have a good sense of motion because your canals are picking that up, and your touch receptors are picking up a mix of both of those. Now my second condition is what I call the on the back condition, my space flight analog condition. And in it, what I do is I take people and I just tilt them so that they're on their back, just like this. And all the dynamics are exactly the same, okay? It's inverted pendulum dynamics. If you do nothing, it sort of falls to the left or right, and they have to stabilize themselves around that balance point. Now the reason why I call this a spaceflight analog condition is that if you remember in the upright, the further you got from the balance point, the more those hairs deflected. But when you're on your back, those hairs are just saying, hey, you're on your back. And you can be at the balance point or 10 degrees or 20 or 30 degrees away. It doesn't matter. Your otolith hairs are just saying, hey, you're on your back. As a result, you can't use gravity to figure out how far away you are from the balance point. So you don't have a good sense of your angular position. The only information that you have in this condition is motion information. How fast are you moving, what's your acceleration, things like that. And this is similar to what astronauts may experience as they go from 0G and are starting to now enter into Mars or the moon. Now, this is the first collaborative juncture because I promised all of you that I'm going to try my best to make this interesting to a variety of different fields. And there are a lot of labs at Brandeis that look at animal models where you deprive the animal of some sensory information. And what I would almost recommend or put out there is that think about maybe doing vestibular deprivation. A lot of people look at vision. What about vision and vestibular deprivation? There's literature on there, but it only takes a few steps to get into completely uncharted territory. And I'm really happy to do the literature search and brainstorm these ideas with anyone that may be interested. Now, because this is a holistic presentation, I'm not going to give you actually a lot of data. This is going to be one of the few graphs that I'll show, and if you kind of memorize it, that will be good because I'm going to refer back to it. And this is just a summary metric. I have a lot of metrics that I use, and this is just one of them. So on the x-axis is block number. Block 1 is early in the experiment. Block 5 is late in the experiment, about 40 or 50 minutes in. And my experiments are wicked simple. You just go in the machine, just try to balance to the best of your ability, minimize that variability. That's pretty much all you're doing. This group is the upright group, the people who have a good sense of where they are in space. And the metric I'm showing you here is a standard deviation of angular position. And all that means is how much variability do you have around that balance point. In the beginning, you can see these people are all over the place, quite high standard deviation. And as time goes by, you can see that there's a classic learning curve, and statistically, they're able to reduce that quite a bit. Now let's take a look at people who are on their back in that spaceflight analog condition. What's going to happen? And again, I expected people would be worse. I did not expect that people would be 2 times as bad. And really, what surprised me was that what I didn't expect even more was that they're in this machine for 50 minutes, and statistically they're not able to reduce that variability. That blew my mind that they're stuck in this purgatory, a frustrating purgatory from which they cannot escape unless they say, get me out of here. And they're not able to reduce this as a group. Now, I kind of want you to emotionally connect to how crazy this is, because 90% of people say, man, this is one surreal, unusual experience of my life. I have no idea where I am in space. Some people report vestibular illusions where they feel like, and I actually feel this even though I know everything that's happening, you feel like you're spinning around 360 degrees even though the machine can only move plus or minus 60. That's the range that it's programmed to move in. So it's really weird. And this is my next sort of interesting collaborative juncture, which is that, from the psychology point of view, what happens when you take away a critical sensory piece of information? And one idea, as the brain is rapidly trying to piece together its reality, once this piece of information is missing, maybe one idea is that it does sensory reweighting. And one thing I forgot to tell you is that another illusion that some people report is that when they're in this machine, some of them ask, like 10% of them ask me, am I completely upside down? And I'm like, whoa, like, you're on your back, you've got touch receptors on your back telling you you're on your back, and yet you're feeling like you're completely upside down? That's insane. And one idea that I have as to why that might be the case is they're wearing a 5-point harness, and that maybe is pulling down on their shoulders, and they've reweighted their tactile information, and so now they feel like maybe they're upside down. It's kind of insane. And so this, again, even for people that study animals, where some of this stuff may be hard to figure out, it's an interesting, deep question to ask. Like, what are the individual differences? And are these interesting vestibular illusions, are they based on internal models and prior experience? Or is it something inherent to the physiology of their vestibular system? If we give them more feedback or we give them training, can we change some of these things? And another interesting neuroscience idea that I think would be really fascinating just to even talk about is, can we induce these sorts of illusions in animal models? And honestly, I don't think there's a lot of literature on that while we're recording from them. And again, there's a lot of philosophical questions, like how do we know if an animal is spatially disoriented, right? But these are things I think that are worth talking about and dreaming about and exploring. So if you're interested, definitely reach out. Now, another interesting perspective, which I take from the skilled motor learning literature, which may be useful for some of your data analysis, is what people in motor literature say is that don't ignore the motor variability. Don't just throw away that variability and say, hey, that's noise, it's trash. What they say and what they actually successfully use is they use that motor variability, they look at the structure within that motor variability, and they use it as a window into central processing. If you're interested in a few examples of that, feel free to ask me at the end. So using that perspective, I go back to this graph over here, which I showed you before. And again, to refresh you, that red bar over there are the people on the back who have huge positional variability and are not able to statistically reduce it over time. And my question is there any pattern within that, or is it just randomness because they don't know where they are? And it turns out, fascinatingly enough, there actually is a pattern within that variability. And again, what this is kind of saying is, don't just look at averages and standard deviations. Sometimes deeper in there is structure. This is raw data. This is for people in the upright who have a good sense of where they are. This is trial 20, the last trial. On the x-axis is just time. The black line is angular position. This is just what the machine is doing. And you can see this, and the green line, I should say, is a 0-degree point. That's what they're trying to do. You can just see as time goes by, the person, she goes a little bit to the right, a little bit to the left. She's within 10 degrees, just doing a great job. She's mastered this task. Now I take the same person and I put her on her back for the 40-50 minutes and see what happens. And what happens is kind of extraordinary because there's a pattern, and that's a pattern of positional drifting, which is characteristic in every single person who's on their back. And what happens is she starts near the 0-degree point, but then she gets further and further away as time goes by. She begins oscillating at 20 degrees as if that were 0 degrees, further, until bam, she hits the crash boundary. And then majority of people say, I had no idea. I was so far away. So that's kind of crazy if you think about it. Now, what I can also do, and I'm not sure if there, is to sort of excite maybe, or maybe even seduce some of the homeostatic and dynamical systems people, is I can take this raw data and I can replot it as a phase plot. And again, talking about all the details of the phase plot would take a while, but what I'm going to do is just quickly give you just one or two things to think about. So the phase plot, for those of you that don't know, I take trial data, and at every time point, I just ask, what is the position, what is the velocity? What is the position, what is the velocity? And I take that and I splash it onto this graph here, where on the x-axis is position, on the y-axis is velocity. Again, all I want you to take away from this is circles. there's circles there, right? And those circles are centered around the origin. And that origin is the balance point, the gravitational vertical. And I can kind of say that, look, this is analogous to an attractor point, where you have orbits around this central point. I could also analogously say, maybe, that this is like a homeostatic set point. You're always trying to restore yourself to it. Now again, I'm being a little bit loose with these words, but the objective of me being loose with the words is to encourage discussion, exploration into similarities and differences. Now, I can look at the people on the back, and what happens on the back is really interesting, because that attractor point, that homeostatic set point, it shatters across the position axis. And now you've got all of these, you could say, shattered attractor points, and you sort of oscillate around those for a bit, and it begins to drift across that. So again, I would love to collaborate and collect examples of attractors breaking, or homeostatic set points breaking in different systems and examining what happens. I would just love to do that. So if any of you want to, let me know. Now, continuing this sort of like, seduction, I could say that I can take people in the upright where they have a very good sense of where they are, and I can transition them by pitching them back onto the back where they don't know where they are. And I can ask this sort of physicsy question: at what pitch angle does the phase transition from single to multiple attractor states happen? So it's interesting, right? Is there hysteresis, another physicsy word, if you go from upright to the back and then back to upright? And I can ask even more interesting questions, like at the threshold, can I nucleate attractor points by flushing it with noise or other sensory information? And again, I feel like there are connections here to a whole variety of other fields. Okay, so I'm just trying to showcase that this is an interesting paradigm that has many different applications. Now, the next thing I want to talk about is I start wondering about maybe the neural mechanisms to a certain extent of this positional drifting. And to again reorient you, this is another person, another experiment. On the x-axis is time, the green line is a target, the 0 degree point. The person does not have gravitational cues, so does not know where they are to a certain extent, and then they begin to drift away, further and further and further away until they hit the crash boundary. And the question now that I asked, and I'm not going to talk too much about this study, I'm packaging together a paper, so if you're interested in this perspective, let me know, and I'm happy to talk more about it later. But basically ask people to trigger press, press the trigger button every time you felt like you were at the balance point. And one hypothesis is that they knew that they were not at the balance point, they just couldn't balance it. But the other hypothesis is that maybe their perception itself is changing. And what we find is, sure enough, these little purple dots are showing that their perception is changing. This person, right at the jaw of, to be dramatic, the jaw of death, this is the crash point, right? Right here, they are thinking, oh, I'm just at the balance point, it's so nice. But really, they are going to be hitting the crash boundary, within a little bit. The other thing I kind of want you to notice about this is it's insane how quickly they lose sense of where they are. I mean, within 10 seconds over here, they're already about 20 degrees error in their self-perception of where they are. Now, if you look at the literature on angular path integration, what they say is that, well, we have neural mechanisms to take acceleration and velocity, send it to a neural integrator that integrates the velocity over time to make an estimate of position. And there's experimental evidence for this, there's theoretical, evidence for this, and the very convenient and perhaps correct answer is that there's error accumulation at every integration step that is accumulating, which is causing this positional drift. But what's interesting is that if you then look at the actual models of the vestibular system, these models don't predict the rate of error accumulation or positional drifting that I have. So for anyone that may be interested, with a computational neuroscience background or something and wants to work on this, I would totally be down to this, to update some of these models to include what I see in my data. Now, another interesting sort of neuroscience, computational neuroscience, stuff like that, collaborative idea is that there is literature on angular path integration in other animal systems like flies and mice and rats, of course humans, and possibly whatever this creature is on my finger over here, because all of these things require angular path integration. So the next 2 or 3 papers I'll show, I actually haven't read in super detail, but if any of you are interested, reach out to me and we can open up a ice cold kombucha virtually and talk about, these ideas, and I'll do detailed literature search then, because I think they're fascinating. So this is a paper on flies, and they take the fly, it's walking on a ball in a virtual world, and when you turn the virtual world's lights off and it's complete darkness, while recording from the fly, they find that there's drift in the angular path integration. And in my work, again, we see positional drifting. And in my case, the landmark is the gravitational vertical, because that's what's calibrating the canal signal that's coming in. Another example, this is a theoretical example, and I actually reached out to Sam and we had a discussion. He's mad chill. And he said that, who knows, maybe there's a possibility that this is what's happening in humans. So in his models, which I believe is based off of rat data, he has this bump attractor model. And the idea for path integration is that, as you're integrating, you're moving from one cell or cluster of cells in this ring structure to the other. And if you take away landmarks and you put the animal in darkness or whatever, take away the otolith signal, you do see a drift in this model, which is interesting. And what's even more interesting is that they've done experiments with moving rodents in a large open arena, where if the rodent doesn't see the boundary and there are no landmarks, while they're recording from the grid cells, they find coherent drift in the grid cell pattern. So this is interesting, So if you're interested in talking about it, I would love to explore these ideas further. Now, I'm coming close to the last segment of my presentation. And coming back to this graph that you saw before, again, the red line here is the people who are on the back in the spaceflight analog condition. And just to remind you, this is a standard deviation of angular position, and collectively as a group, they're not able to reduce this variability, as time goes by. And I could be like, okay, end of story, right? This is done. My average in standard deviation is not changing, and therefore they didn't learn anything. But, and this might be interesting for some of you to think about in your data, one idea is that what if I go into this data set of everyone on their back, where statistically there doesn't seem to be a change, and then look at them and cluster them into different groups, okay? And to do that, I used a machine learning technique, and I created a partnership with Peng Yu, who's a really awesome computer science professor here, and his undergrad at the time, he's now graduated, but Han, a brilliant guy, and we did machine learning stuff. And I'm only going to concentrate on one storyline of the few that we developed. So we used machine learning, we looked at the people on the back who were in the spaceflight analog condition. And the first thing which I was surprised were there were a few people, a group of people who I call the proficient group, who actually learned across all metrics. Now again, performance-wise, they weren't very good, but still, they were learning as time was going by, which was crazy because they didn't have gravitational cues to do the task. What was the secret? And I'm not going to talk about that storyline, but it eventually led to like a training program where we thought about balance having two disassociable components. So this is another story for another time, and if you're interested, totally ask me. The story that I will talk about is the even crazier finding, which is that the people who were doing very, very poorly in this task, okay, and just to explain how poorly these people were doing, they got into the machine, right? Huge oscillations, understandable, but by the end of the experiment, they're just smashing back and forth, going absolutely insane. It was frightening. I thought the machine was going to break. Okay, so what was really interesting about this group was that they were not randomly bad. They all were doing the same suboptimal strategy, and there was one piece of improvement. Everything else got worse, but one thing they learned to improve, which was avoid the crash boundaries. So somehow by going crazy really fast, they were able to avoid hitting the crash boundaries as often as they were in the beginning. Okay, so what's really interesting is that okay, so let me just quickly describe what the strategy was. So if you look over here, the top group is the proficient group, the ones that could do it, and all I just want you to look at is the red line, which is joystick. You can see the joystick is like small deflections. It's very varied, diverse. And you look at the people in the not proficient group, and they grab the joystick and they just Hulk smash, just smash as hard. This is as hard as you can possibly deflect the joystick. They're just smashing it, and it's very regular, very stereotyped. Okay. So now the psychology question is, what's really interesting that every single person in the not proficient group was doing this. So the question is that, okay, this is a suboptimal strategy. It kind of works. Why did these people not explore the full solution space? And again, this is relevant for all of our lives. If you're playing basketball, one question is, Why do some of us get stuck at suboptimal strategies and that's all we do? And others keep expanding until they find the global max solution where they're able to shoot perfectly. Why is this individual difference happen? And quantifying mathematically the solution space is a really interesting thing if any of you want to collaborate on that. One idea anecdotally, just by talking to people, is it may be that the people who do this technique have greater anxiety. They smash, it kind of works, and then they just stick with it, and they're too anxious to be able to explore the rest of the solution space. Okay, now one of the last things I kind of want to say, which may be relevant for some of you that study oscillations, is that I wanted to quantify mathematically that the joystick deflections in the bad group over here were very stereotyped, not any diversity, just really like a pendulum back and forth. How to do that? So to understand that, I reached out to Jonathan Tabul, who's a really amazing math professor here, and then Se Wung, who now is a professor at University of Texas in San Antonio. And they both use Hilbert transforms, which give you the instantaneous phase. And I ultimately just compared the instantaneous phase of the joystick with the position. I'm not really going to go into too much detail on this. The reason I'm bringing this up is that, we all study oscillations to a certain extent. How cool would it be if we did a lecture series, or we got together and we created a toolkit of how we approach oscillations? So if any of you are interested in that, let me know. I'd totally be down for that. Now the final story is I'm funded by this really awesome organization, Trish, and they're in a cooperative agreement with NASA. And so all of the things I do have to answer NASA's roadmap, risks and gaps and things like that. And so the next stage of my research is looking into the technological countermeasures for spatial disorientation. This ultimately means human augmentation, adding sensors to enhance human performance and learning. And I'll give you a quick example of this. So this is like, back in the day, this is just one example of many, right? And this is sensory substitution by Baki Rita. And what he did is he had a camera attached to a blind person, and that camera then outputted what it saw as a series of shocks on the tongue. And so on the tongue, you had like a 100, two-dimensional matrix of little shockers that you put on your tongue. So if the camera sees an X, you get an X-shaped, shock on your tongue. And what he was able to find is that, surprisingly, people who are blind were able to avoid obstacles, would kind of detect shapes, could catch a ball if it's being thrown at them. It's kind of interesting, okay? But what's also interesting is that these types of experiments are being done in animals. So, in this rat, I think they implanted some sort of infrared sensor or something right into the brain, and the rat was able to detect infrared. So it's interesting, right? This is a newly burgeoning field, and if you're interested in these topics, feel free to reach out on that. What I'm planning on doing is using tactile stimulation to replace the missing gravitational cues from the otoliths so that I can rescue performance on the back. Now, the problem is that I can't make this device because Brandeis doesn't have an engineering school, so what do? And what I did is, with a collection of really cool people, we created this group. And what we do is we just get together, learn how to use Arduinos and sensors and actuators, and then we help one another on our research projects. So if you're interested in joining the group, it's open to everyone. Just reach out to me, go to the website. We meet every Thursday. I also do educational outreach with high school students. If you're interested in that, reach out. I also have a mythological universe, and I shaved off all of my hair, and the mythological universe has research that comes into it. So if you're interested in that, feel free to talk. Appreciation for my advisors, and then of course my lab, and then any questions.